Hey guys, today we're going over gas laws for Avogadro's law and combined gas law. All right, so follow along and we'll get through this. Okay, so first thing we're going to talk about is Avogadro's law. So make sure you're on the side that says Avogadro's law. It describes the relationship between volume and moles. All right, it is, let me move the mouse. Okay, it is should just be a direct relationship. So what that means is if the volume increases, then the number of moles also increase or vice versa. Okay, very exactly the same thing as Charles' law. All right, so an example is you have a balloon that only has a few molecules of air in it, and then you start blowing air into the balloon. And when you do that, you're adding a whole lot more molecules. All right, so a flat balloon has very little moles in it. Okay, I'm saying molecules, but I mean moles, they're kind of interchangeable right now. All right, so the flat balloon has very few moles in it. A blown up balloon has a lot of moles in it. All right, so again, this graph is very similar to the Charles law graph. All right, we'll have the volume as dependent, moles as independent, and as you blow more air into the balloon size increases, so that's where the direct relationship comes from. All right, this equation is written as the volume in number of moles that you initially start with. So this is your before. And it's equal to the same ratio of volume and moles afterwards. Oops, sorry, that should be into V2 into. Okay, so your before and after. All right, again, the ratio stays the same. All right, so we're going to go ahead and jump on into the sample equations. Remember, this is very similar to Charles' law, so we're not learning a new type of math. We're just putting in different numbers, okay? A sample of gas occupies 2 liters with 5 moles present. What would happen to the volume if the number of moles is increased to 10? Okay, so just like what Ms. Carpenter did yesterday, the first thing that we're going to do is we're going to list out what we have. Okay, so it gives us our first volume in moles, or our initial volume in moles, as 2.00 liters, and the moles was 5.0 moles. All right, and then what would happen to the volume? So we're trying to figure out what happens to the volume if the number of moles is increased to 10 to 10 moles. Okay, again, when we're talking about moles, we're talking about adding particles to something. Okay, all right, so this is the units that we're starting with. The second thing is, are all of these units in the correct form? Well, we need volume to be in liters. Volume is in liters, okay? And N stands for moles. We already have everything in moles. So number 2, all units are good. So we can go ahead and give that a check mark. And jump to the third part, which is where we take the equation and we plug stuff in. Okay, so our equation is the initial volume in moles is equal to the same ratio of the final volume in moles. All right, so that would be 2.00 divided by 5. I put that in parentheses, I didn't have to necessarily. We're looking for the second volume, and it gave us 10 moles. Okay, so with Charles' law yesterday, we cross-multiplied. Let me change the color so you can see what I'm doing. We're cross-multiplying. Okay, so we're going to have 2 times 10 is equal to 5x. This is a lot easier to get x by itself. Okay, so now I can divide by x on both sides. And when I do that, I do 2 times 10, so it's 20. 20 divided by 5 is 4. So x is equal to, we'll say 4.0. And since this is a volume that we're looking for, our unit will be in liters. Okay, so this is what we got. If you want to double check what you got to make sure that you're on the right track, then what you're going to do is you're going to look at your two variables. Okay, so we have moles and we have volume. We know both moles. Okay, when we start at the beginning and finish at the end, our moles has increased from 5 to 10. Okay, and then we figured out that the volume was 4.0 liters. So we started at 2 and says we moved up to 4, so that one also increased. All right, so as one increased, the other increased. That's exactly what's supposed to happen. Okay, so that's another way that you can double check that you're correct with the gas laws. Okay, so sorry, I'm sniffing. Ugh. All right, let's see. So the next example says, what happened to the number of moles? Okay, so we're looking for a number of moles in a sample that originally occupied 500 milliliters with 250 moles, and then occupied 750 milliliters. Okay, so again, first we're going to list out what we have. It tells us that we originally had 500 milliliters in 2.50 moles. And we're looking for what happened to the number of moles. Oh, okay, and then occupied. So our second volume is 750 milliliters. And we're trying to figure out what happened to the number of moles. Did it go up? Did it go down? Did it stay the same? I don't know. Let's do math. All right, so the second part, we need to make sure our units are in liters and moles. All right, my moles are in moles, okay, but my liters are not. So I need to change my V1 is in 500 milliliters. Remember the shortcut that we learned yesterday? Or not yesterday, Wednesday. Wow, Wednesday with Miss Carpenter. Okay, is we're going to move the decimal 3 spots to the left to go from milliliters to liters. So this is going to end up being 0.5 liters for V1. Okay, so V1 is 0.5 liters. We're going to do the same thing for V2 because when we look, that is also in milliliters. Okay, so 750 milliliters. We're going to move the decimal to 3 spots to the left. So my V2 is now 0.75 liters. All right. So now I've got all my units where they need to be in liters and in moles. So we can jump over to step 3. All right, again, with this equation, here, I'm just going to do the equation in orange. V1 over N1 is equal to V2 over N2. So when I plug my numbers in, that's going to look like 0.5 over 2.5 is equal to 0.75 over x, because I'm just doing everything, whatever we're looking for is x. All right, since we have two fractions, to get x by itself, the easiest thing to do is to go ahead and cross multiply. So we're going to cross multiply, and that's going to give us 2.5 times 0.75 is equal to 0.5x. So now to get x by itself, if we divide it by 0.5 on both sides, when you put this in the calculator, you're going to do 2.5 times 0.75 and then divide it by 0.5. All right, and that will get you x equals 3.75, and we were looking for moles, so that's going to be my unit. And again, to double check, so we had 3.75 moles. Okay, we had both volumes initially, and it went from 500 to 750, so my volume increased. My moles went from 2.5 to 3.75, so my moles also increased. And if both are increasing, then we're on the right track, so we are good to go. All right, so that's Avogadro's law. Hopefully I didn't go too fast, but make sure you have this written down because it's an excellent reference as you go through the assignments and the quiz and the reviews and the test. All right, now we're going to talk about the combined law, or the combined gas law. All right, so for the combined gas law, it combines all three of the gas laws that we've been talking about. So Boyle's, Charles, and Avogadro's. All right, for a sample of gas and the ratio, so the ratio of the product of the original pressure, volume, temperature, and moles will equal to the ratio of the product of the new pressure, volume, temperature, and moles. So again, what that's saying is however much you start with is going to be the same ratio of what you end with. So the numbers might change, but they all change at the same rate. Okay? The equation for the combined gas law is your original pressure, volume, moles, and temperature is equal to your new pressure, volume, moles, and temperature. Okay, so again, this is the before, and this is the after. All right, the units pressure most of the time is going to be in atmospheres. You just need to get used to seeing pressure in atmospheres. Sometimes you can see it in millimeters mercury, sometimes you can see it in kilopascals. Temperature still needs to be in Kelvin, so where you see degrees Celsius, make sure you add 273. Liters is still in volume. N still stands for number of moles. All right, let's jump into some sample equations. Okay, if I have 17 liters of a gas at room temp or at a temperature of 67 degrees Celsius and a pressure of 88.89 atmospheres, what will be the pressure of gas if I raise the temperature to 94 degrees Celsius and decrease the volume to 12 liters? Okay, and it's asking for the pressure. So first step we're going to do is we're going to list out all these variables, and it's a lot of variables. Okay, so we'll read through the question again. If I have a volume of 17 liters, okay, so that's my initial volume, 17 liters, at a temperature, so my initial temperature is 67 degrees Celsius, and a pressure at 88.89 atmospheres. Again, most of the time it's going to be in atmospheres. What will be the new, or the pressure, so what will be the new pressure, the after pressure, that's what we're looking for, of the gas if I raise the temperature to 94 degrees Celsius and the volume to 12 liters. Whew, that's a lot of variables. All right. But what do you notice isn't there, but is in our equation? Moles. This problem says nothing about moles, but moles is in the equation. Okay. So this is a note that you need to add, and I would just add it up here. Okay, I'm gonna say no mention of moles, okay, which is represented by the letter N. Means we can leave moles out of the equation for this problem. All right, I know that's a lot to write, but go ahead and write it down. All right, and it's not going to be moles every time. Just for this first example, there's no moles. All right, so if it doesn't mention a variable at all, you can leave it out of the equation when you get to the equation part. Okay, so no mention of moles means we can leave moles out of this equation for this problem. All right, so number one, we've listed out our variables. All right, for number two, we're going to make sure everything's in the right unit, okay? Volume is in liters. Temperature, however, is in Celsius. So 67 degrees Celsius plus 273 is equal to 340 Kelvin for my new T1. All right, pressures in atmospheres, that's good. Looking for the second one. Second temperature is in 94 degrees Celsius. So when we add 273, that's going to give us 200 and nope, sorry, it's looking at the wrong problem. That's going to give us 367 Kelvin for second temperature. Okay, so now I've got all my units in the right, all my variables in the correct unit. Okay, so now I can look at the equation. So the initial equation is P1 times V1 over N1 times T1 is equal to P2 V2 over N2 T2. Okay, now what did we say over here? That it does not mention moles anywhere in our variable list. So that means that I can just take moles out of the problem entirely. Okay, it's like it never existed. All right, so now what I'm going to do is I'm going to plug in the numbers that I do know, and then we'll continue solving it from there. All right, so we know the pressure was 88.89 atmospheres initially times 17 liters over 340 Kelvin. And that's equal to X, because we don't know the second pressure, but we do know that it was at 12 liters. Oh, I'm not writing the units. Okay, 12 liters over 367 Kelvin. Okay, so this is what it looks like when I plug in the numbers. Now I'm going to solve for X. And again, since I have fractions, the best thing to do here is to cross multiply. Okay, so we're going to cross multiply. And when we do that, it's going to get us, let's start over here a little bit, 88.89 times 17 times 367 is equal to 340 times 12 times X. Okay, so again, now I have everything in one flat line, so it's going to be a lot easier to get X by itself. How would I get X by itself? Divide by these numbers. So we're going to divide it by 340 and divide it by 12 on both sides of the equation. All right, so now I can plug this into the calculator. when I plug in the calculator, I'm going to do 88.89 times 17 times 367. I'm going to divide it by 340, divide it by 12 since they're both on the bottom. And when I do that, I get X is equal to 135.9 atmospheres. All right, so this is my P2. All right, just like we double checked with the last one, with all of the laws that we've been learning about with Boyle's, Charles, and Avogadro's, we know the relationships, how they're supposed to be. So if I chose something like Boyle's law, okay, Boyle's was Boyle's said that as pressure increased, the volume decreased, okay, or vice versa. It was an indirect relationship or an inverse relationship. We want to make sure that's happening with our units. Okay, so here, the initial pressure is 88.89, final pressure is 135.9, so my pressure has increased, okay? And then, so now we're looking at volume. Volume went from 17 liters to 12 liters, so my volume decreased. So according to Boyle's law, we're doing the right thing, okay? And you can check it with any of the laws. I just chose Boyle's because it dealt with pressure, and that's what we were, that's the only one that we've done that deals with pressure. Okay, so let's go ahead and look at this last example. All right, a toy balloon has an internal pressure of 1.05 atmospheres and a volume of 5.0 liters. If the temperature where the balloon is released is 20 degrees Celsius, what will happen to the volume? So we're looking for the new volume when the balloon rises to an altitude where pressure is 0.65 atmospheres and the temperature is negative 15 degrees Celsius. That seems cold. Okay, so let's go ahead and list out our variables. All right, so it tells us that our first pressure is 1.05 atmospheres. Our first volume is 5.0 liters. And the temperature that the balloon was released at was 20 degrees Celsius. All right, what will happen to the volume? Okay, so we're looking for the volume, that's our X. When the balloon rises to an altitude where the pressure is 0.65 atmospheres and the temperature is negative 15 degrees Celsius. All right, what's the variable that's missing here? No moles again. Okay, so neither of these examples have moles. Moles is the least commonly used one, but it is used sometimes. So again, just whatever you're missing, take out of the equation. Everything else you keep in. Okay. So next, we're checking our units to make sure they're the right units. Pressure is in atmospheres. That's great. Volume is in liters. Even better. Temperature is in degrees Celsius. So I've got to convert that. Okay, so T1 was 20 degrees Celsius plus 273. So T1 is now 293 Kelvin. T2 is negative 15 degrees Celsius plus 273. So T2 is now 258 Kelvin. All right, so now I've got my new temperatures and I can start plugging and chugging. All right, so we have our initial pressure, initial volume divided by the initial temperature, because again, there's no moles, so I'm not even writing moles down in this problem. Actually, I'll go ahead and write moles P2 V2 over into T2. There's no moles, so I can mark moles out. All right, so I'm left with all my pressure, volume, temperatures. And so let's plug and chug. All right, so we got 1.05 times 5.0 divided by 293 is equal to 0.65 x over 258. All right, I realize that I'm not writing in the purple like I have been, so my apologies if that's bugging you. All right, so we're going to cross multiply, so that way we can get everything out in a line. All right, so we're going to have 1.05 times 5.0 times 258 is equal to 293 times 0.65 x. So to get x by itself, we're going to divide 293 by 0.65 on both sides of the equation. All right, and when I do that, my x, all right, so I'm going to multiply 1.05 times 5 times 258 divided by 293 divided by 0.65. And that's going to give me 7.11 liters, okay, because that's the volume. Unit is liters. All right, so 7.11 liters. When I double check, I'm going to use Boyle's law again. So what we're looking for is pressure increases, volume decrease, or vice versa. Okay, so the pressure here is going from 1.05 to 0.65. So the pressure is actually decreasing. Okay, so what that means is we want to make sure that the volume is increasing. So the volume goes from 5 to 7, so it is increasing. So for Boyle's law, we are good.